Good afternoon, student. Today I'm going to discuss in this video how to calculate the moment of inertia of a section. So I will first start with the very basic understanding of moment of inertia, which usually covered in class of statics. If you have taken the statics class before, you should be able to recognize these equations that I'm going to derive. But if you have forgotten, if you want to review, for class for solid mechanics, where you have to calculate the bending stresses in beam and also to find the shear stresses, where you need to calculate the moment of inertia, and also you have to calculate the moment of area. But in this video we are going to discuss only on the moment of inertia. So I'm going to draw a very basic sections, and then we'll go from there, the basic understanding of it. Let's say I have this particular coordinate system. I have x here and I have y, right? So let's say I have this body, any arbitrary geometry. What I'm going to calculate is the moment of inertia of this particular object. Let's make inside of this body. So let's color it, so we know that this is the body that we are interested in, and or object we are interested in. Let's say we are going to create a small area, small patch here, small area like this. So we are interested in finding the moment of inertia of this whole body, and we assume this small dA area. This is the dA, a small area, elementary area, which is at a length, at a distance of y from x-axis, and at a distance of x from the y-axis. So the moment of inertia we write in this form: moment of inertia with respect to x. That means moment of inertia with respect to x means the object is going to rotate about the axis x. So the distance of that small elementary area is y. So we take an integral, and y square into dA. This is the moment of inertia about with respect to x-axis, and moment of inertia with respect to y-axis is x square into dA. Okay. Now this is the basic and fundamental definition. Now if we change this object to a square object, let's say I want to calculate the moment of inertia of a square. Want to draw a simple square, no, not a square, sorry, rectangular area. Okay, so let's say I have this rectangular area, and I want to find the moment of inertia of this particular section about the neutral axis with this one. Okay, so this is my neutral axis. Why this is neutral axis? Because this is my center of area. That's why the axis passing through the center of area is called the neutral axis. Now I am interested in finding the moment of inertia of this rectangular section. I just define the geometrical parameters. So let's say this is b, and this is the height, which is h. Okay, now I would use the same process. I will take a small elementary area here, which is this much. Okay, now and we will assume this is the y-axis. So we will assume this is the y-axis. So this distance is basically dy. Then this small the elementary area is basically nothing but b into dy. Okay, now we are interested in moment of inertia with respect to, let's draw with a different color so that it is more prominent. We are interested in moment of inertia about this green axis. So moment of inertia with respect to the neutral axis is basically then the distance of this small elementary area of y, so which is y square into dA. What is dA? dA is b dy. So let's multiply with b dy. Then I have to do this integral. B is here, and I have to perform this integral that y is changing. So we have to change the y from minus h by 2 to plus h by 2, right? So minus h by 2 is the negative axis, and then the positive axis. My x-axis, y-axis starting from here. So minus h by 2 to plus h by 2, I have y square dy. That gives me b into y cube by 3 minus h by 2 to plus h by 2. Plus h by 2. If you substitute the values of y with h by 2 minus h by 2, you will get this is b h cube by 12. So this is the fundamental equation for moment of inertia of a rectangular section about an axis which is passing through the neutral axis and passing through the neutral axis which is at the center. Now let's say if that same axis is passing through a new line which is axis from here, which is another axis, then we are interested in finding a new axis. Let's say, let's name this axis new axis A. So we are interested in finding the moment of inertia with respect to this blue axis which is IA. Then how do I find my moment of inertia with respect to this is y plus d whole square into dA, where d is the distance of this guy. Y plus d whole square into dA. Now the same way, if I substitute this, then we get d into y square plus 2yd plus d square into dy. We get dy square dy plus 2yd into dy plus d square. D square is constant, so it can come outside. D square and dy. So I also have a b dy here because each and every one is multiplied with b. So I have a b 2yd. Now this one is to a moment of the area with respect to the center. If you see, this y is with respect to the center, and that can be neglected, so that is 0. So this is b y square dy plus this whole thing is nothing but the integration of the area. So the total area, integration of a strip over the total area, that means the total area of the section, which is here in this particular case is a rectangular section. I can write b into h and d square. So this is the total area of the section into d square, and this part is the what we found with respect to the central axis. So b h cube by 12 plus b h into d square, which is in this particular case is h by 2, so whole square. So we get b h cube by 3. So this is the moment of inertia of the section with respect to the blue axis, and the moment of inertia bh cube by 12 with respect to the green axis. Now if you recognize that this is the moment of inertia with respect to any centroidal axis. So this is the moment of inertia with respect to the centroidal axis. In order to move the centroidal axis to somewhere else at a distance of d, then we write a into d square. This is what we found. This is a and this is d square. So generalized way, we can write any arbitrary axis moment of inertia is equal to the moment of inertia with respect to the centroidal axis plus area of the section into the distance between two axes. So which is, and here in this particular case it was neutral axis and the arbitrary axis A, so it can be any axis. If that blue axis is somewhere in between green and blue, which might be a separate color, like say this purple color, not it did not pick up the purple, let's say this one, the purple color. So if I want to find something about this axis, then we just have to use the distance between these two axes as d here and the cross-sectional area A. So but the moment of inertia with respect to the C is the this moment of inertia with respect to the neutral axis always. Okay, Now this gives me a basic idea of the formulation of the rectangular cross section, how to find the moment of inertia. Now let's find an example formulation for finding the moment of inertia of a I section, like a basic I section. Pardon my drawing, but this is the, let's say this is the thickness of the flange, like TF, and this is the thickness of the web, CTW, and this is the width W of the flange, and this is the height of the web, so HW. Okay, so you must recognize that what I'm calling them is the web. This is the flange part, this is the flange part, and this is the green one is the, if you see, this is the web part. Okay, so in the web part we have a height HW and the thickness TW, whereas flange part WF and TF, and they are same on both sides. Now my neutral axis, if the section is symmetric with respect to this axis, so this is, let's say this is my centroidal axis, and as I use the green as my centroidal axis, let's use the green color. So this is my centroidal axis, neutral axis. So I have to find my moment of inertia NA, which I also called moment of inertia with respect to the centroidal axis. That means it is lying at the point passing through the center of area. So IC is equal to moment of inertia of the yellow sections plus the moment of inertia of the green section. Let's find the moment of inertia of the green section. If you see, the moment of inertia of the green section can be found easily using the rectangular section formula that we just derived, BH cube by 12, because in this particular case, for the section of green, the axis is passing through the center of the area. So that means I can write TW as my B, HW as my H cube by 12, BH cube by 12 for the green area. Okay, so this is my moment of inertia of the green section, moment of inertia of the green section. Now let's write down the moment of inertia for the yellow sections. So moment of inertia of the yellow section will be B, which is B means width, WF, H cube, because TF cube by 12. But this formula valid for an axis which is passing through this centroid of the flange part, but that is not the moment of inertia of this section which is passing through this green color. So I need to have a formula that is for parallel axis theorem. If you see, this particular formula that we discussed here is called parallel axis theorem. Here I have the moment of inertia with respect to this section, this axis, black one, and I need to find the moment of inertia with respect to the green section. So I have written the moment of inertia with respect to the black section. Then I need to add AD square. Here A, what is the area of the yellow section? Area is WF into TF, that is my area. And D square, what is D square here? The D square is the half of the HW. I can clearly see from here. Let me take a different color with a little bit smaller. I can clearly see from here to here, this is HW by 2, right? And half of it also is TW by 2. That is the distance of the centroid of this yellow area from the CG, which is CG of the whole area that is on the green axis. So that I can write TW by 2 plus HW by 2, that is by total D whole square. So that is the moment of inertia with respect to the centroidal axis which is the green axis. Now, but we are not completed yet. This is one section, that is only the top one that we have calculated so far. If you see that, now let's mark with the proper marking here. So we have this one, this one. However, I have two of these sections. Which will not change, because moment of inertia with of this yellow section, which is at the bottom, can be the same thing, and the distance of this section with the green one is the same thing. So I just multiplied these two to accommodate the two of these sections. So if you substitute all these numbers given to you for this particular I section, you can find it. Now I am not going to discuss in this video, but if you have a I section which is not symmetric, then you have a sections like this, maybe, where this is not symmetric. Let's say you have a bottom flange is much bigger than the smaller top flange. Then it is possible, it is obvious that the center of area is somewhere lowered here. In this, it is not dividing the section half and half. The distance from the top to bottom, they are not same. So this height h, let's say ht and hb, they are not equal. That means you have to find this center of area. And how to find center of area? Those are very basic fundamental the fundamental theorem that can be easily found using the balance of areas. Like you have this particular area is A1, this particular area is A2, this particular area is A3. Then the CG with respect to any axis, like say this is my axis. From here I want to find where my CG or the center of area is located. I can find using y prime with the total area, which is A1 plus A2 plus A3. Let's say this is the total area AT, and AT can be written as A1 plus A2 plus A3. These are actually covered in statics class, so I'm just going to quickly go over this part. AT into y prime will be equal to the A1 is the area, but how far this CG is from here to here is, let's say, the distance is D1. So that is D1 plus, let's say, CG of, or the center of area of A2 is at a distance of D2 from the same axis from here. So which might be somewhere, if you see, this is the center of the A2, so this is D2, and this A3 D3, which is from the same axis, this CG of this guy is somewhere here, so this is D3. Okay, so if you have calculated this 3, area multiplied with distance, area multiplied distance of 3 composite areas, and try to find the centroid of the whole area, you can find y prime by dividing this AT by this equation A2 D2 plus A3 D3 divided by AT. Then you can find the center of area very easily. Once you find the center of area, then you use the theorem, parallel axis theorem, to transfer the moment of inertia of each section to that centroidal axis using the formula of moment of inertia with respect to the centroidal axis plus A into d square. That will help you to find the moment of inertia of any I sections, but these are only for the rectangular formulations, rectangular sections. But for moment of inertia of a circular sections and triangular sections, that can be found using this similar type of integral, but those can be found in several books. If you want to cover, please send me an email or comment, so then with that we can discuss those in a separate video. So thank you for watching, and hopefully this calculation will be very helpful.